acids, bases and salts topic. I want you to learn these definitions that are going to be in red, and I actually want you to do that. It will help you in the long term. I know people are resistant to doing learning, but you learn vocabulary for languages, you need to learn definitions for chemistry, and unless you do so, you won't be brilliant at the subject. So let's start with what an acid is. And the main thing I want you to understand about an acid is that acidity, all acidity, is down to those ions there, hydrogen ions. And not just hydrogen ions, but hydrogen ions, the AQ represents in water. Hydrogen ions in water is acidity. If you've got a lot of those, then that is very high acidity. And if you've just got a few of those, that is alkalinity. So it's measuring the quantity of hydrogen ions that will really get you to grips with what acidity is. And therefore, I want you to learn the following definition. Acids. Acids, what are they? They are chemicals that form hydrogen ions when dissolved in water. Now, different syllabuses have different definitions, but that, as an idea, fits all syllabuses. Some syllabuses want you to know that acids are proton donors. And look, if you've got an acid, that is a proton. Hydrogen atom with an electron removed is a hydrogen ion. That is H+, is a proton. And when an acid makes those things, we talk about that acid being a proton donor. And you can learn that. You can learn acids are proton donors, and that gives you all the marks in exams. But for understanding purposes, I want you to learn that red sentence. What are acids? They are things which, when dissolved in water, give you hydrogen ions in the water. Example is hydrochloric acid, HCl gas, hydrogen chloride gas. The hydrogen chloride, if I just put that to one side, then I can talk like that. The hydrogen chloride gas dissolves in the water and makes hydrogen ions and chloride ions. The arrow there is a forward arrow showing that all of the hydrogen chloride gas we start with, all of the gas, when it's making hydrochloric acid, all of it turns into ions. It completely ionizes. And that's the idea of a strong acid. Strong acids are acids that completely ionize in water. The examples of strong acids are three very common acids: hydrochloric, sulfuric, nitric. They are the strong acids. We use them over and over again. And you will have come across these acids. You will have come across them in the topic on reactions of acids. No, I think this is the topic where you'll really use those acids. But you have come across these acids when we've reacted metals with them. And we've reacted metals earlier when we were looking at patterns of reactivity, and reacting metals with them gave salt and water. And we're going to look at them again in this topic. But they're the strong ones. Now, weak acids. You will have come across weak acids or carboxylic acids when we did organic chemistry, and one of the homologous series was carboxylic acids. And the most famous of our carboxylic acids is ethanoic acid. That is ethanoic acid. Remember, the common name for ethanoic acid is vinegar. So vinegar is an example of weak acid. And the definition of a weak acid is that weak acids are acids that only partially, like a couple of percent of what you start with, turn into ions. So if we start with those molecules, like 1% of those will turn into ions when we put it in water. 99% won't. 99% stay as the molecules of ethanoic acid. And with these things, we draw reversible arrows to show that they are partially ionized. So weak acids are partially ionized. Now, if they partially ionize, then the quantity of hydrogen ions will be much smaller, and the reactions are therefore slower, and the indicators are giving you colours where the acidity is shown to be less than the strong acids of the world. Okay, so learn those things in red. These are responsible for acidity. I've said that. Now, 4 indicators you need: litmus, methyl orange, phenolphthalein, and I would say universal indicator as well. I've got them here to show you, but this diagram gives you the colours in a really nice way. So, litmus. We use litmus in 2 varieties. There's blue litmus and red litmus. And blue litmus is used to test for acids. And in an acid, blue litmus goes red. And red litmus, believe it or not, is used to test for alkalis. And with alkalis, it goes blue. So there are only really 2 colours of litmus. Blue for alkali and red for acid. Phenolphthalein, that's one of my favourite. It's my indicator of choice when I do titration. But phenolphthalein, again, 2 colours. In acids, or neutral, or less than 7, in neutral and acids, colourless. In alkalis, is red. Red and colourless, again, 2 colours. Methyl orange, 2 colours. In acids, red, and in alkalis, and neutral, it's yellow. You need to learn those colours. Those are the indicators, and then we've got universal indicator. Universal indicator is a variety of colours, starting with strong acid being red, weak acid being orange. When it's very close to neutral, it's yellow. At neutral, it's green. Weak alkali is greeny blue. And strong alkali is proper blue. And I would learn universal indicator colours on top of those. Now, here I've got the 4 indicators: strong acid, weak acid, water, weak alkali, strong alkali. What colours would we get? Practice filling that table in. You need to know these colours. And if you look at the last slide and then fill this in, you will see that they are the colours. Litmus, red and blue. In pure water is reddy blue. They don't ask you that in pure water, but it's like both colours mixed up together. Methyl orange is yellow but red in strong acids. Phenolphthalein is red in alkalis, otherwise colourless. And universal indicator, red, orange, green, greeny blue and blue. Learn those colours. Now, pH scale. Now, let me just cover that up while I talk. My phone went off there. I was talking about pH scales. So, pH scale is a log scale. Now, the main log scale you may know about is earthquake Richter scale. When we hear of an earthquake that is like Richter scale 6, earthquake scale 6 on the Richter scale, that's quite a major earthquake. when we hear of a Richter scale 7 earthquake, that's not just a little bit more than 6. That's 10 times more powerful. Each 1 unit is 10 times more powerful. So Richter 6 earthquake compared to Richter 7, the Richter 7 earthquake is 10 times more powerful. Richter 8 is 10 times, again, more powerful than a Richter 7 earthquake. And it's that kind of scale, a pH scale. So you've got the number 2 in terms of acidity, and the number 3 in terms of acidity. Well, the pH 3 acid is less acidic. But it's not just less acidic by a bit, it's less acidic by a 10-fold decrease in acidity. So the pH scale 2 is 10 times more acidic than the pH scale 3. And I want you to understand that it's not a linear scale, it's not just normal numbers. Now, pH, which we do calculations at A level, but we won't do pH calculations at GCSE, but the pH is a measure of the concentration of these blessed hydrogen ions that are in the water. So measuring their concentration, that's how many moles you have per litre of solution, measuring their concentration, working out how many moles per litre of hydrogen ions in water that you've got, is what pH scale is all about. And you guys should know, you've tested unknowns, and you guys should know the pH scale spans from 0, acid, through to 7. 0 to 7 is acids, 7 is neutral, and 7 onwards up to 14 is alkalis. A pH value of 0, we will do moles per litre calculations in year 11. So I want to just throw out to you that a pH value of 0 represents a 1 mole per litre concentration of hydrogen ions. A pH value of 2 represents a 10-fold dilution. So you take 1 part of a acid, the pH value 1, take 1 part and add to it 9 parts water. That means you're diluting it 10-fold. Then the pH will change from being 1 to being 2. Again, it's that same point I started with. It's a log scale like a Richter scale. Lower pH values, lower the pH, the more acidic it is. The pH like the Richter scale, when we move 1 unit, represents a 10-fold change. I've been wittering on about that. The values of pH for solutions above 7 are alkalis, below 7 are acidic, and pH 7 represents neutral. So that's a pH scale. Now, I like to represent the pH scale as a V. Watch. There, that's my V. Now I've drawn that in my own way. And I want you to know the 7 is neutral. There. And this side is acid, that side is alkali. And there are 4 examples I want you to learn and know where to place them on the pH scale and know what they are as examples, because you are asked to give examples of a strong acid. Now, strong acid, I want you to learn hydrochloric acid. Here, look, hydrochloric acid. That is the example I want you to have in your head whenever anybody asks you, give an example of a strong acid, I want you to pick that, hydrochloric acid. It all turns into ions when you make it, and the making of it is hydrogen chloride gas in water. So that's water where hydrogen chloride gas has been dissolved into it. That is strong acid. Now, the pH of strong acid, 0 or 1. Right about there, 0 and 1. They are typically the pHs we have for strong acids. Weak acids. Now, those pH values are closer to 7. And the example I want you to use is ethanoic acid. There, vinegar. vinegar solution. That's ethanoic acid. Ethanoic acid. It will have a pH value of about 5 or 6. And learn that. pH 5 or 6. Neutral. At room temperature, neutral is pH 7. That's not true at all temperatures. It's true at room temperature. Now, the other side, you want an example of weak alkaline, example of strong alkaline. And the example I want you to learn for weak alkali is ammonia solution. Look, ammonia solution. Learn that as your weak alkali. And ammonia is a gas. Put it in water, it makes an alkali. And it partially turns into ions. It doesn't fully turn into ions. That's why it's a weak alkali. What fully turns into ions is a strong alkali. Now, strong alkali, I want you to learn sodium hydroxide. Now, sodium hydroxide is something that turns into ions completely when dissolved in water. And I want you to learn the pH of 14 with sodium hydroxide, and I want you to learn the pH of about 9 with ammonia, 8 or 9. Now, you may or may not like that representation. I don't care. I want you to understand it. Having understood it, then you may prefer it in the form of a table. I'll let you decide. But you need to learn those 5 chemicals as examples of strong acid, neutral, weak alkali, strong alkali, and learn the corresponding pH values that are roughly lining up with which chemical it is. Obviously, the exact pH will depend upon the exact concentration that you're given, but rough pH values are there in that last column, and learn them. So, okay, I've explained what acids are. Let me go on to explain bases, alkalis, salts, etc. I want you maybe, sorry, can I just change this around a bit? So, I'm right-handed. Perhaps I can do that. Bases. Well, I want you to learn that bases react with acids. Bases react with acids, and they make salt and water only. So that top red line is the definition of what a base is. Learn that definition of base. Base is anything that reacts with an acid, making salt and water only. You must put the word only in to get the full marks in an exam. The bases of our world are metal oxides and metal hydroxides. Metal oxides and metal hydroxides will always react with an acid. All right, reaction might be slow, but they'll always react with an acid, and they will always make salt and water only. So the metal oxides, metal hydroxides are the bases of our world. And these are the bases. I've just picked 2: zinc oxide, sodium hydroxide, metal oxide, metal hydroxide, with acid makes salt and water, with acid makes salt and water, and therefore they're bases. Bases, some will dissolve in water and some won't. Well, the ones that dissolve in water, they are the alkalis of our world. Look, learn that red sentence there. Bases that dissolve in water are alkalis. Now, I like to show that in a Venn diagram. So here, we've got the universal set E, which is all chemicals of our world. The bases are clearly a subset of all chemicals, and the alkalis are a subset of the bases. With a key there, you should understand that representation, that all alkalis are bases, but not all bases are alkalis. The alkalis are special bases because they are the ones that dissolve in water. what does the term salt mean then? So I've explained acids, bases, alkalis. Now let me explain what a salt is. I have done this before, I think, but I'll do it again. If you have the formula of an acid and you replace the hydrogen that you've got in the formula of an acid with a metal. So when a metal replaces a hydrogen in the formula of an acid, then you've got a salt. I did this when we did patterns of reactivity, when we were reacting metals with acids earlier on in Year 9 work. So if you've got hydrochloric acid and the metal replaces the hydrogen, you're going to get a metal chloride. To get a metal sulfate, you'll have to start with sulfuric acid and get a metal sulfate. Metal nitrates are salts of nitric acid. Metal ethanoates will be salts of ethanoic acid, and so on and so on and so on. There are thousands of acids, and consequently there are thousands of salts, because any metal, instead of the hydrogen that breaks off when you've got acidity, any metal that replaces the hydrogen that breaks off will make a salt for you. A metal replacing the hydrogen in the formula of an acid will make a salt for you. So if we want chlorides, we've got to start with hydrochloric acid. If you want sulfates, you've got to start with sulfuric acid. If you want nitrates, start with nitric acid. If you want whatever salt, look at the negative ion. That will tell you what acid you need to start with, because the metal will always be positive ion. The negative ion comes from what acid we need to make it. Now, common misconception. I gave a test to my Year 9s the other day, and one of my lads wrote, for definition of salt, it flavours food. I despair, but not to worry. Household salt, that's salt you put into your food, flavours food, is one of many thousands of chemical salts. So it is a salt, yes. It's sodium chloride. Sodium chloride is one of our salts. But there are thousands of other salts in chemistry, because the definition of salt is that thing there in red. So how do we make salts? Most of this topic from now on will be concerned with doing reactions that make salts. And to get you to understand the making of salts, then we're going to throw at you various different methods of how you might make salts. And the least important of those methods, the least important, is this one: direct combination of elements. So say you want to make household salt, which is a salt. Say you want to make sodium chloride there. You could make it by burning sodium in chlorine gas. Burning sodium, an element, in chlorine gas, an element, the two elements join together, they combine, they make sodium chloride. You could make it like that, direct combination of elements. Now, if you do, then that's a really expensive way of making it. Sodium's expensive, chlorine's expensive. Burning sodium in chlorine, really expensive way to make something that is very cheap, like salt. So, this method, rarely ever do I ever want you to talk about it in an exam. Occasionally you get the odd question, like, elements joined together make that, is it a salt? Yes, of course, it's a salt. But you wouldn't make it that way. You'd make it some other way. Just quick diagram of how you would do it. This is chlorine. Can you see the green tinge? And if you put a deflagrating spoon in and you burn some sodium where I'm pointing, that sodium burning in chlorine that will give white fumes, and the white fumes are little particles of salt that happen inside that reaction vessel. And when it's over, if you get your finger, put your finger in the sides of the flask and move your finger up and taste that. That is salt, that is sodium chloride. Now, I'm not saying you do this. We don't taste things in chemistry in the labs because we can be never sure what poisonous chemicals were on that glassware before we started. So we don't taste things. But I'm saying to you, there is a famous Open University video where a man does this, and he does stick his finger in. He pulls out the white sodium chloride salt that's made, and he does taste it. And that's why I mention it. Perhaps I should stop mentioning it from now on. 1 minute, lads. Let me just, that is a message there. I don't want that to shut down. And in fact, probably the most important slide of this presentation is there are 4 general reactions I want you to learn. Those 4 in red, learn them. And they're there. They will be used in this topic to make salts. Look, an acid and metal make salt and hydrogen gas. We've done that previously in year 9. The metal has to be reactive enough. If you remember, copper and below copper do not react in the reactivity series with acids because they are not reactive enough. Acid, base, all bases react with all acids. Acid alkali, all acids react with all alkalis. Acid carbonate, all acids react with all carbonates. So just be careful, the metal is reactive enough. But when these react, they make salt, 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 salt. With metal you get hydrogen. With the base that's got oxygen in it, you get hydrogen with oxygen making water. Alkali, again, the hydroxide, it's got the oxygen in it, with hydrogen makes water. And with a carbonate reacting, you get carbon dioxide gas and water. Those 4, I cannot tell you just how important those 4 general equations are. Now in year 9, I think I covered about 5 or 6 general equations. 4 more general equations here, take you to about 10. And they are our stock general equations that we use to do various reactions at GCSE that we want you to write about, talk about knowledgeably, do balanced equations for, etc. As I've said to you before, chemistry is not random. We're not just going to ask you any kind of reaction. We're going to generally pick a reaction that is within the realms of GCSE, one of these general equations. Either one of these 4 or one of those previous 6. Give you about 10 general equations in all. Learn them. It will be good for you. Having learned them, you'll then be able to do normal chemistry and be good at chemistry. So these reactions can be used to make soluble salts. Now soluble salts are salts that will dissolve in water. So those are used to make soluble salts. Well, what about salts that don't dissolve in water? Well, we have a particular method for how we do that. And my next video will be a method called precipitation, where I explain the first of our 3 main methods for making salts. And we'll do precipitation next video. But this video, there are my 4 general equations, and in my handwriting I have written examples. Example: hydrochloric acid with magnesium makes salt and hydrogen gas. Nitric acid with copper oxide makes salt and water. Sulfuric acid with sodium hydroxide. Acid alkali makes salt and water. Acid and carbonate. Hydrochloric acid with calcium carbonate makes salt, water, carbon dioxide. You need to practice any combination of common acid with common metal or base or alkali or carbonate. And here, I would pause the video, I'd do loads of practice writing these equations, because these reactions can be used to make soluble salts. Now, there is a general flow diagram like this, and I'm going to introduce you to two such flow diagrams, but making salts is what pupils find pretty hard, knowing what method to use, and I'm going to introduce you to three methods, and you can come back and look at that if you want, but I will display it again in the next video, and I'm going to focus on the next video. Is the salt you want to make, is the salt soluble or insoluble? Now, if it's insoluble, that means it does not dissolve. If it does not dissolve, you want to use that method, precipitation method. And I'll be picking up from that point next lesson. Take care. See you then.